Welcome to our tutorial video on sets. This is a video to introduce students to the concept of subsets and power sets. Aside from learning these concepts in this lesson, we will also be investigating some patterns to come up with generalizations to help better understand subsets. But before we continue, it is assumed you already know the basic concepts of set types, cardinality of sets, and basic set relationships. Also, if you're confident enough to skip to other parts of this video, you can click the timestamps in the description below. Let us discuss subsets. Now let's look at the definition first. Set A is a subset of set B if we meet a certain condition, and that is, if every element of A is also an element of B, which means A is part of set B. Okay, now let's look at certain pairs of sets here below. We are given set A with elements 1, 2, 3 and set B with elements 1, 2, 3, 4, 5. Let's look if one is a subset of the other. Looking at element A first, check. Is 1 part of set B? Yes, it is. 2 and 3, if you notice, are also parts of set B. Therefore, we can say that these three elements are also part of set B. Every element of A is part of set B. We can say then that A is a subset of B. Now, how do we write that in mathematical form? We have a symbol for subsets, which is this one. It's actually a letter C, and below it is a horizontal line. Now, we write it in mathematical symbols as A is a subset of B. Now, does it work the other way around? If A is a subset of B, can we say that B is a subset of A? While this is true, let's check the second statement. If B were a subset of A, every element of B should also be in A. B should be part of A. Let's look at every element. 1, check. We also have that in A. 2, check. We also have that in B. 3, we also have that in A. And then finally, 4 and 5. Are 4 and 5 part of set A? No, they're not. Therefore, we cannot say that B is a subset of A. So, that means subset, that relationship, is not necessarily commutative. Meaning, if A were a subset of B, it does not necessarily mean that B is a subset of A. Now, let's look at the next pair. For example, we have C, QRS, and set D with elements QRS as well. Looking at the definition, will one be a subset of the other? Check every element. Q, which is in C, is also in D. R, which is in C, is also in D. Finally, S, which is in C, is also in D. That means every element of C is also in D. Therefore, we can say C is a subset of D, which can be symbolized as C is a subset of D. Now, from the first example earlier, we said that A is a subset of B, but B is a subset of A is not true. How about in our second pair? Check. Is D a subset of C? Let's see. Q, is that also part of C? Yes, it is. The second element of DR, it's also a part of C. S is also a part of C. That means every element of D is also in C. Therefore, can we say that D is a subset of C? Yes, it is. We can write that in mathematical form as D is a subset of C. Now, notice in this case, unlike the previous pair, where the relationship subset is not commutative, in the second pair, it is true. As you can see, these have exactly the same elements. How do we call these sets again with exactly the same elements? They are equal. We can say that C is equal to D. Now, what can we generalize? If C were equal to D, then C is a subset of D, and D is a subset of C. So, the relationship subset is commutative if we have exactly the same sets. We can further say that a set is a subset of itself. Last pair. Now let's look at the third pair of sets here. We have set E, which has no element, is obviously the empty set, and set F with two elements, the colors green and red. Now, let's check. Is set E, the empty set, a subset of set F? This one is a little tricky. We'll attempt to answer this by thinking out of the box. First, note that set E, being empty, has nothing in it. It has no element. Then, let us go back to the definition of a subset, therefore asking the question, is that no element a part of set F? We can answer this by attempting to combine, sets E and set F. Combining set E, the null set, and set F with elements green and red, we have green and red. That means the no element is now part of set F. But the resulting set, which is still the same thing, green and red, is practically the same as set F. Which further means that this no element is actually there in set F. It is part of set F all along. Actually, we can observe the empty set with other sets. Check natin. If we combine set E, the empty set, with set A, for example, 1, 2, 3, we will have the same number of elements, or we will have the same elements 1, 2, 3. Therefore, set E is part of set A. Check natin sa set C. If we combine set E with set C, QRS, it will be the same QRS. We can deduce then that set E is part of set C all along. So, we can generalize then that the empty set is part of any set. Thus, the empty set is a subset of any set. Going back to our statement here, we have concluded that set E is a subset of any set, in this case, set F. Now, is the other way true as well? Meaning, is set F a subset of set E? Now, let's check. Are green and red part of set E? Of course not. Therefore, this is not true. Now, finally, generalizing all of these pairs of sets, we notice that subsets are only commutative, meaning it will work the other way around if the two sets are the set itself, meaning only this case is true. When two sets are exactly the same, then the relationship subset is commutative. We can flip that relationship. Subsets have two types. The first one is called the proper subset. Now let's define what a proper subset is. A is a proper subset of B if, aside from the definition that all elements of A are in B, basic definition of subsets, we should satisfy this more important condition. B contains at least one element that is not found in A. Ibig sabihin nito, B has more elements than A. Let's look at the previous example to illustrate. We have set A, which has elements 1, 2, 3, and B, 1, 2, 3, 4, 5. From our previous slide, we know that A is a subset of B. Hence, we use the symbol subset. But can we be more specific? If we observe, aside from 1, 2, 3 being part of B, we can see that we have extra elements here. We have at least one. We have 4 and 5. To be exact, we have 2 extra elements. Therefore, A is a proper subset of B. So that's being more specific. Now, the symbol for proper subsets is this letter C here. We can then write A is a proper subset of B. So again, let me be very clear. This statement is true. A is a subset of B. But if you want to be more specific, since there are extra elements here, we can further say that A is a proper subset of B. Both statements are true. Now, let's check our third example from the previous slide. We have the empty set and set F, which contains green and red. Well, again, from the previous slide, we know that E is a subset of F. This, we know, is part of this set. E is a subset of F. But can we be more specific? Is there an extra element in F that is not found in E? Yes, there are. Again, we have two. We have green and red as extra elements of F compared to set E. That means we can be more specific and say that E is a proper subset of F. F has extra elements. Now, we can then be very clear. We can use this symbol meaning subset. That is true. But we can be more specific. E is not only a subset of F, but a proper subset of F. This is true. Now, here's a tip. Notice this symbol. It looks like a very important concept in mathematics that you're familiar with. It can roughly look like this less than sign, isn't it? Which means if we rewrite this, we can write it as E. Instead of using that, we can be more specific. It looks like that. Which means that E has less elements compared to F. F is the bigger set. Therefore, E is less than F, which actually looks like this one. So that is your clue. If you want to be more specific, we can use this symbol, which means one set is sort of less than the other. Now we have the second type of subset, and that is the improper subset. Now, when is a set an improper subset of the other? Let's say we have set A is equal to set B. We should know from our previous examples that all elements in A are obviously also in B. Thus, A is a subset of B. We know that from the previous slide. But if you want to be more specific, A is an improper subset of B. Now, what is the symbol of A is an improper subset of B? It's easy. It's the same as the symbol for subsets. Now, looking at our second pair here, we know they are equal. We also know that C is a subset of D, and D, since they are equal, is also a subset of C. Is C a proper subset of D? No, it's not. Because C, take note, is not less than D. They are actually equal in number. So this is not a proper subset, is actually an improper subset. C is an improper subset of D. Clue in this case, parang equal sign, ano? So C is sort of equal to D. Actually, if you look at these three pairs, remember from these examples below here, that there is only one improper subset of any given set. It's the set itself. There are no other improper subsets. All the others, they are proper subsets. This time, let's investigate and let's try to write all the subsets of the set below. We have set Z here with only 3 elements, 1, 2, and 3. Now, if our aim is to completely list all subsets of Z, it is best to organize our list and not just write sets randomly. You may have your own method to do this, but let me show you mine. My plan of attack here, is to start listing from the subsets with the least number of elements. We know, of course, that the null set is a subset of any set. Let me list it here. It's the first subset of Z. Next, let me increase the number of elements and list all subsets of Z with only one element. 1, 2, and 3. These three sets are also part of set Z. Next, let me list all subsets of Z with 2 elements this time. I'm starting with 1, 2. My technique here is to partner 1 with 2 first, then partner it with 3. Element 1 done. Next is partner 2 with the other elements. I'm writing 2, 1. But there is a problem here. This is actually the same as 1, 2 above. It's the same subset. So let me erase it and partner 2 with 3 instead. Remember that we cannot write 2, 2 since the elements of the sets should be distinct. So element 2 done. Next is to partner 3 with the other elements. I'm writing 3, 1. But we have listed 1, 3 already. And they are the same. Let's erase that. I'm partnering 3 with 2 this time. But again, we have listed 2, 3 already. And they are the same. Let's erase that again. This further means that we're actually done listing all subsets of Z with 2 elements. Finally, we list the subset of Z with 3 elements. We know, of course, that there is only one possibility here. It's the set itself. Also, we can recall that this is the only improper subset of set Z. All these other subsets are proper subsets of Z. Let's have another set this time. Set A with 4 elements. More elements, more exciting. Same plan of attack. List all subsets in increasing order of elements. Let me quickly write the subsets with no element and 1 element. Next, we list all subsets of set A with 2 elements. I'm starting with 1, 2. Partner 1 with 2 first, then partner it with 3, then with 4. Element 1 done. Next is partner 2 with the other elements. As we have learned from the previous set, we partner 2 with 3, then with 4. Element 2 done. Next is partner 3. We should know that 3, 4 is the last 2 element subset of set A. Next, let me list all subsets of set A with 3 elements. I'm starting with 1, 2, 3. By observing, only the element 4 is not on this list. Thus, on my next subset, only the element 3 is missing. Let me write it here. Do you get my pattern? The next subset, only the element 2 is missing. Next subset, only the element 1 is missing. 3 element subsets done. Finally, we list the subset of A with 4 elements. It's the set itself. Also recall that this is the only improper subset of set A. All these other subsets are proper subsets of A. Now, our aim is to investigate and learn from these 2 examples. Let's count the number of elements of set Z. As we know, this number of elements is the same as the cardinality of Z. It has 3 elements, which we can call n. N is then equal to 3 for set Z. We can also count the number of subsets of Z. And we see that there are, you count them yourself, there are 8 subsets of Z, 7 of which are proper subsets, and only 1 is an improper subset. Let's look at set A this time. The cardinality of A, or the value of n, it has 4 elements, thus n is equal to 4. That's for set A. We can also count the number of subsets of A. You can count them yourself, do it fast, and we see that there are 16 subsets of A, 15 of which are proper subsets, and only 1 is an improper subset. Now, let us copy this data in the next table to further investigate. Now, let's plug in the values from the previous slide to this table. This might seem a little intimidating, but let me try to explain what this means. On the first column are different sets and with different number of elements. We should be very familiar with set Z and A here, as these were just discussed in our previous slide. On the third column, here are the proper subsets of sets Z and A, which were simply copied again from the previous slide. The proper subsets of sets X and Y are already shown, as they can be easily provided by organized listing. On the fifth column is the list of improper subsets of sets Z and A, again derived in the previous slide. The improper subsets of sets X and Y can be easily provided, since the improper subsets of X and Y, we should know this, are the sets X and Y themselves. Now the challenge is, can you complete this table? Are you up to the task? Get your notebook now and answer. You can pause this video as you try to complete it. Kaya yan! Go! Here is the completed table. Did you get the same? Now let's have some more observations. By looking at this part of the table, this confirms that there is only one improper subset of any set, the set itself. Now, let's look at this part. We can observe that the empty set W is the only set with no proper subset. It has only one subset, and it's the improper subset, the set itself. Interesting. Now, let's look at this column and also this column. As the cardinality increases, these red values, the total number of subsets, these green values, also increase. These two values are actually related, and this is by using the formula total number of subsets is equal to 2 raised to the nth power. Let me isolate these two columns, the red and green, and put them in just one table, and let me explain how this formula can be used. Now let's complete the second column and use the formula 2 raised to the n and see if we can get the total number of subsets. Now let's start with the easiest one, this row. Now if n were equal to 1, then 2 raised to the nth power is equal to 2 raised to the first power, which means 2, which is, yes, it's equal to the number of subsets, 2. Now, let's increase the number of elements, taking n is equal to 2 this time. We substitute n is equal to 2, therefore 2 raised to the second power means 2 times 2, therefore equal to 4. Again, it's correct. It's 4 here as indicated by the number of subsets. Next, let's try 3. We have 2 raised to the n, or 2 raised to the third power, which means 2 times 2 times 2, which is of course equal to 8, again equal to the number of subsets from the previous table. Now let's try 4. 2 to the nth power is 2 to the fourth power, which is 2 times 2 times 2 times 2, which is equal to 16, again equal to what we have counted from the previous table. Now, let's look at 0. Interesting. 2 to the n is 2 to the 0, which is, oops. This may be a little advanced for us now. But just for now, let us memorize that 2 raised to the 0 or any number to the 0 is equal to 1. Don't worry, we'll get back to this on the second chapter of our lessons. But again, memorize any number to the 0 is equal to 1, which is again consistent to what we have counted from the previous table's subsets. Now with this formula, we can actually get the number of subsets of any set even without listing all the subsets, just like what we did with sets Z and A. The formula works, use it confidently. Finally, we go to power sets. So, what is a power set? Let's look at its definition first. If I may read, the collection of all subsets of set A is called the power set of A and is represented by PA. Now, you read this as the power set of A. And as we can see, it's a collection of all subsets. Take note, collection means a set. That means it's a set of subsets. To illustrate, let's look at set Z, again from our previous examples. We know that set Z has 3 elements, and here are its subsets. Now, what if we're looking for the power set of Z, indicated by PZ? Now, since power set is the collection of all the subsets of Z, then we write our 2 curly braces first, and then use the subsets, all of them, as the elements of this power set, as you can see here. So this is the power set of Z, the set of all subsets of set Z. Now, finally, we can also get the cardinality of the power set of Z. How do we get that? Cardinality, take note, is the number of elements. But in this case, the elements are the subsets. So when you want to get the cardinality of the power set of set Z, we simply get the number of subsets of set Z. And how do you do that? You use the formula 2 raised to the nth power. Or, let me write that in formula form. The cardinality, indicated by n, of the power set of Z is equal to 2 raised to the n. It is equal to the number of subsets of set Z. And if we would like to compute that, it's 2 raised to the nth power. N is 3 here. It's 2 to the third power. Therefore, 8. The cardinality of the power set of Z is 8 because it has 8 elements. And these elements are the subsets of set Z as listed above. I hope marami kayong natutunan. See you on our next video. Happy solving!